Today we're taking a look at a game of Boggle, and we're going to write a Boggle solver. The game of Boggle is played out on a board 4x4 with random letters. You're giving a limited amount of time to find as many words as you can. The rules state that you're giving 3 minutes. All the words must be valid. They must be at least 3 letters in length. All letters must be connected either horizontally, vertically, or diagonally. No individual letter cube may be used more than once, and no capitalized or hyphenated words are allowed. Most Boggle solvers scan the board and build all possible words, relying on some form of prefix tree to reduce the search space. And it works really great, especially noticeable on bigger boards, something like 100 by 100. But it complicates the solver, and we want to build something simple to not rely on any tree-related data structures and keep it similarly fast at the same time. As it turns out, we can reverse the traditional solution, and instead of building all possible words on the board and then verifying whether the word is valid based on some dictionary, we can grab that dictionary, and for each word in it, we can simply check whether the word can be found on the board or not. Surprisingly, it works really well, and it is quite fast. But again, I have to remind you that this solution works well only on smaller board sizes. If you want your solution to work fast on bigger board sizes, you have to learn about prefix trees. Now, this is everything about the rules. So let me showcase you the game itself. We're going to be using a terminal version that runs in Linux. It is installed using BSD Games package, and I don't know whether you can run it on Windows or Macintosh, but pretty much everyone can run Docker containers nowadays. So that's what we're going to be doing as well. So let me run a slimmed down Debian Linux using Docker run, interactive mode. I will remove any previous installation if I have any. Debian, bookworm, I think it's slim, and we're going to be running bash. We will update our package index and install BSD games. Once everything is installed, we can check where the Boggle game is. We can do that using the packet manager request to show us all the files from BSD games package, right? Except that we need to find our Boggle game. And it says that the Boggle game is in user games Boggle. When we start the game, the timer starts, the board is here, we can type in the words that we find. So let's try to find a few. Something like wake. Like B. And bike. Now, there is a help section which tells you about some commands. We will use one of those commands, Control D, which stops the game, so it doesn't wait for the timer. And once the game is finished, it tells you the amount of words you found and the amount of words and which words you missed on the board. Each of these words can be found on this board. Ideally, once our solver is ready, we should be able to find all these words, input them, and none of them or the game will tell us that we've missed none of the words. I guess this is enough about Boggle game itself, and we can start with our solver. So as usual, we need to first create our repository. Let's create new one and name it something like simple Boggle solver. We'll add some basic readme. I don't know, like whether we need to add some Python git ignore or not. Yeah, I'll skip readme as usual and provide it later on. Once the repository is created, we can then clone it. Let's get inside, touch our Boggle view, and let's write our main function. So def main start here. As usual, I'm gonna create an alias to help out running this program. So br, like for Boggle run, Python 3, and it works just fine. All right. So what I want my solver to do, I want it to accept two arguments. First being the board, which is represented by a single string. Pretty much if we have a 4x4 board, it will be a single string containing 16 characters. First 4 representing the first row of the board, second batch of 4 letters representing the second row, and so on. Now we also want our solution to work with different board sizes. That's why we're going to define a board size and make sure that it's used everywhere where we rely on board size. So changing this value will make it work for different board sizes. To work with arguments, we need to import sys first, and then first thing that we need to check whether if sysargv, I think length is not how many? 3. We can say, hey, oh, no semicolons, like usage Python 3 Boggle board dictionary. So we want to receive a board representation and a path to dictionary. You will see like why quite soon, and we can return or use return here. So if we run our alias, it instantly says that hey, we're missing some arguments. So let's update our command, say xxx, run it again, and it successfully passes this check. Next, we need to verify our board string. Right, so board string is what? It's sysargv1. We can strip it and then check whether the length of this board representation is correct. We can check it using this, like if the length of board isn't equal to board size, we can say error board string must contain characters board size times board size, and we can format it this way. Let's run it again. We get an error. We need to update our alias once again. 16 or no? Yeah. All right. run it. Now it passes. Next we need to get our dictionary path. So dictionary path is rank v2, which we strip as well. I won't be doing any checks or try-catch blocks. I simply, for simplicity, assume that the path is correct. So we can open this dictionary path in read mode and then read all the words from it. Let's see. It's gonna be saying dictionary is a word. Yeah, we can also strip it and probably, or let's do lower, not upper. And then the board string, we can also use all lower cases here. Now, let's run the Docker container again. I think because we're running it and I'm using the run flag, I need to install the game again. Now the thing is, once the game is installed, I know for sure that it's using a dictionary which is located in user share dict. And it's using this words, which is symlink to American English. We want to copy that dictionary from Docker container to our project directory. Simple Boggle server. Let's see which container is running. Our bookworm slim. Let's get its ID, and then we can use copy command from user share dict. I think it's American English to this folder. Successfully copied. We can again kill this. Kill the Docker, and let's take a look at the dictionary which we just copied. Right, so you can see that it not only contains the valid words, but there are also some capitalized ones like names, some abbreviations as well, but in the end it also contains all the lowercase letter words. So what we really want is probably to not grab all the words, but we want to check if the stripped down word is alpha, right? So it uses all the letters and is lower, right? So we're simply skipping all the words that contain capitalized letters or which are hyphenated. Let's print out the dictionary and see what we get. First of all, again, let's update our alias and say it's going to be American English, the file that we just copied from the Docker container. And let's run, and looks good. Except that I see there is a one letter word which we need to also avoid. So we need to tell that the strip down the length of the word must be 3 or greater. And let's run it again. And no more single letters or two-letter words, which is great. We can stop doing that. We can say that, okay, results, please solve, yeah, just solve my board string in dictionary. This is going to be a different function. Solve, we receive a string and we receive a dictionary. which is a list of strings, and we return the list of all found words, which in the beginning is going to be empty. List is unknown. We need to import that from typing, from import list. All right. So once we have all our results, we can print it out. We can save and join results like that. If we run it, because we are returning empty array from our solve, we print empty line here. So let's think. What should we do when we're trying to solve the board? First of all, we need to build the board from string representation. Let's think like what the board is going to be. It's going to be a dictionary which takes some sort of position and a character. Yeah, because Python types don't have character, we need to use strings here. Dictionary is built-in thingy, and position is going to be tuple. Some tuple as well. Pretty much it's a row column tuple position, and the board is a dictionary given some position, row and column. There is a character there. So board is going to be build board from the given string. How do we build that? Let's see. It's going to return a board. This is how we return a dictionary, and now we need to tell it that hey. We're going to return some key with some value, which is a character for a in range, which is like board size time board size. So because we know that the length of the board is board size squared, I needs to go over all this whole range from 0 up to board size squared. We need to grab each character and then convert I into row and column. And this is done by division without remainder, by board size and modulus by board size, so the remainder. Let's print board to see how it works. Alright, our board, our alias is actually like all x's, but we can see that each x is now under specific key of row column 0, 0, 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, 1, 2, 1, 3. Yeah, looks good. The board is built. Next, we can say that really like our dictionary contains all possible words, and the board contains only some limited amount of letters, at least on a smaller board sizes. So we can do something like candidates. We're going to filter our dictionary in a way that if we have some letters, which is like board values, so this is like all the letters on the board, and candidates is going to be so for in dictionary, so for each word in dictionary, all of them are currently candidates, but we want to filter something out. So if the words, this start the first character of the word in letters, pretty much we're saying that, okay, dictionary, give me all the words where first character of the word is present on the board. If it's not, then 100% we won't be able to find the word there. Now that we have candidates, we can say that let's return word in candidates. It returns all the words, but we need to check if board has word. The board itself and the word. What is this board has word function? We have board, we have word, and it will return bool. Let's say false, right? So pretty much for each candidate word, we are asking the board, hey, can we find this word here or not? Let's think. We have board, we have word. We're gonna say like this. So first, do we need that? Not really. So we need to iterate over. Let's say start position and character. In board, what is it? Items. So items is going to return position and the character in that position. We're saying that if character is equal to word 0, so the beginning of the word is the same as the character on the board, and we can do some depth first search. And if we find the word, then we can return early. If not, then we will try to find other position with the same character. What is this depth first search? It's gonna say that, hey, I need to find what? I need to find something at start position. I need to find the remaining part of our word. Right? Because we already found that the character at start position is actually the beginning of our word. So we're interested in that we're starting here, and we need to find the remainder of this word. And we need to keep track of which cells on the board we have already visited, because the rules state each like cell or letter, but not really like it's a cell, can be used only once. So start position is our visited part. And we can now define this depth first search, and we can define it inside our function. DFS. Position is our position. It's going to be a suffix, right? So the remainder of the word is suffix, and visited is set of positions. And it will return boolean if we can find something. Set. We can import that. And let's see. So we have some suffix. We know the visited, and we have position. So we need to look at all the neighbors of the given position. So as you remember, we can move horizontally, vertically, diagonally to all our neighbors. And we can start searching for the cell that has the character that suffix begins with, and we haven't visited it yet. So first of all, we need to find the neighbors of our position. So let's define a new function, neighbors, given some position. I will return a list of positions. And pretty much we can implement it this way, that I'm going to return a tuple, because position is a tuple, which says row plus row delta and column plus column delta. Row and column comes from our position, right? So we deconstruct it. What is row delta? Row delta for -1, 0, and 1. Column delta is also -1, 0, and 1. We don't want to be in the same position, So we need to filter it out. If not, because if both row delta and column delta are 0, we are checking the same position, but we're searching for the neighbors of this position. And this is not everything. We also need to make sure that this new value, this position, is actually inside the boundaries of our board. So we need to check if 0 in board size and column is also right. So given some position which has like row and column, we want to look at all the cells around it. We need to make sure that we don't generate the same position as we were given as an input, and we want to make sure that this new position is inside the boundaries of our board. This way we generated all our neighbors. Now we can iterate through those neighbors. So for example, for next position in neighbors of current position, if not, if we haven't visited that cell yet and board get the character at that position is equal to the beginning of the suffix, then that's where we want to go, right? So we need to recurse again, saying that, all right, we're now going to next position. We're going to use the remainder of the suffix, and we need to also say that, hey, we're now visited the position. So it's visited, and we're going to next position. Like that. Now what we're missing here is our end condition. So at some point, if the word is actually present on the board, our suffix will be empty. So it means that we constructed the board, it was linked by the nearby cells. So if not suffix, it means the full word was found on the board. And this is like the whole meat, the most complicated part of this solution. Pretty much finding whether the word can be found on the board. And I think this is pretty much it, right? Should be. So it's time to test things out. So first of all, I need to split my screen. And then we need to start our Docker again. I will install the Boggle game once again. I could drop the RM flag and reuse the container with BSD games installed. But oh well, what's done is done. Apt install BSD games. Let's run Boggle game. And let's now try to run our Python Boggle. We give it a board. Left pp in our dictionary. Whoa, that's a lot of words. Let me try to quickly type them in. But seems like we did something right, because everything that I'm typing in works, so it accepts. The main question is whether we missed anything or not. So if the solver worked correctly, it should work fine. Oh, debit, debts, del, dice, dirt, ditch, edit, else. Well, that's unusually high amount of words for such a small board. I don't know, like what TBS and TBSP are. Something about tablespoon, something. Don't think it's a real word, but we kind of know that this game uses this particular dictionary. So because it's in the dictionary, it will be considered to be a valid word by the game. That's why we need to also fill it in. So I think everything. I will use the shortcut Ctrl D to end the round earlier. And voila, we found all the words. So this is pretty much it. As I said before, you can probably make it run for a board of size 10 by 10, maybe even 20 by 20. But as the board size grows, you will see a noticeable increase in running time. And that's when you need to switch the solution to something a bit more complicated, but also a bit more interesting if you haven't touched the prefix trees yet. If you like this project and would like to be notified about my future projects, please do like this video and subscribe to my channel. I'll see you again. Bye.